So just a quick thing which you're asking is that in case, so this will come in your actually flattened PLL. We will deal with that thing in a much more detail, but just for your question, so I have ratio and then a divide ratio. Okay, so FREF means reference and output. Okay, so what all ways can you change F out? So I can vary F out by either changing your reference frequency or changing your divider ratio. Right? Now, the question is, let's say I am having a FC carrier, just let me put it here, carrier frequency is 900 megahertz, and I want to go to either side of the channel. So there are like something 128 channels, 200 kilohertz. So let me just say, let's say you want to go plus minus 50 megahertz. Okay, and you're using, for an example case, I am saying, let's say the reference, this is F out, and your FREF is something as 25 megahertz as a reference, right? So surely you are not going to change the reference because that is coming from the oscillator. What you change is the divider ratio. So first thing is that, so this 125, the divide ratio for this is 336, right? 50 and 60. So you want to change divide ratio from 36 to either 38 or 34. This is what you want to change. And if you, now the whole question is, if you change the divider ratio by this much amount, what happens instantaneously in the PL? So for that, the thing is that, first thing is, what is the requirement? How much time of settling are you giving for the divider? Okay, let's say if you do not have any time limitation on the PLL to settle, you change the divider ratio, the loop parameters and everything will change and you will get the desired frequency. If you are very much concerned about how it is going to change the output directly, then the thing is, so you change by one reference period, so you can say that delta T amount phase error will be that, so corresponding to, so let's say corresponding to two reference cycles, two extra reference cycles, when you go minus 50 megahertz, that delta phase error will be injected on the loop filter and you will see a jump there. Okay, and that will take some time to settle, whatever jump you are, depending on the bandwidth of the loop. That is a more conventional way, you like brute force way you can do it. Now, the interesting part is that when you go from, so give you an easier example, let's say, so I'm just starting this as a clock, okay, and my divide ratio was 2 initially. It will be easier to understand, that's what I'm trying to say. So this is uh, F out and this one is my FREF. So the multiplication ratio is 2, right? I want the multiplication ratio to be 3. So what I want ideally, if I want multiplication ratio to be 3 and I do not want to change my reference, so let me, okay, I will just make 3 cycles somehow. They need to be equidistant, so let me try to be somewhat equidistant. Okay, I want to do this and I change the divide ratio N2 to 3. What is going to happen? You will see a good amount of phase error. Mean when you change from F out to F out dash, you will see a large amount of delta phase or phi error at the input. The instant you change it. Okay, and this phi error then will appear as some large up pulse with a large voltage change, and your VCO frequency will change accordingly. Okay. Now, this I am showing you an example for multiplication ratio of 2:3. Let's consider that you are having a large multiplication ratio, something at least 32 or 64, right? So there, the change delta will be smaller, but that is for a large reference pulse. Can you, okay, if I ask you that what is very much deterministic in this system, means there are some parameters which are random, that's a noise, but the some parameters which are deterministic in the system. When you change divide ratio from n equal to 2 to 3, what do you know the output frequency should be? You know the frequency. You know what the phase error is going to be. Means not the phase error. You know what the phase accumulation rate should be going to be. You actually know, means when I change my, so if I know my FE out equals to 2, right? And if means let's say, okay, so let me just say at this reference edge, you compare with the, means you compare this F out with the reference, and after that you change the divide ratio, right? When you change the divide ratio, you know where the next edge of my clock is going to come and what is the phase error I am going to measure. Okay, so if you let the loop take care of itself, it will take care of it, but with more jumps, means like more errors at the output to settle out. But if you know what you are going to inject in it, you can make use of that. Means you can do that phase correction thing, and you can do only, means this is very well analyzed. You can do that phase correction. No, it's a very it again depends what kind of noise are you looking at it. So first thing is, I would say, how much time do you have for the correction? Okay. Then the other thing is, how fast can you do, or what are the problems does it do it? Does it cause? So what I was trying to conclude from this two or three plots is that there is something deterministic in the system which you know that what phase error the change in the frequency is going to cause. And if you know that phase error, you can go and correct for that phase error here. You can go and correct for that phase error here. So it is again dependent on with how much accuracy can you control. Okay, but these two methods will actually help you to switch as fast as possible. So going by the PFD method, basically having a more, not having a cycle slipping on having a more range, that is actually, that causes more problems than that helps. And the reason is this. So let me say, in case of, sorry, when you had, let's say if you have a wide range of PFD where you say I can accommodate more error, but when you have an error, you basically exercise your loop filter. Okay, and you are exercising a loop filter means you are causing a disturbance in the steady state. So that will take some time to settle. So there can be different ways to do that without causing the PFD to unknown jumps or large jumps. You can correct for that at the input of the PFD so that the input of the PFD doesn't see that large phase error. Now, how it is going to help in the transient means I think that can still be worked out, but making use of this deterministic phase error which you will be having because of the change in the divide ratio will help you to have a faster settling, and it will help you also to have a lesser phase noise in the end. Means the ideal goal is if I correct at both the places, means here, sorry, if I correct for my, means when I change my divider ratio, if I correct for the phase error here and if I correct here, the ideal transfer function is all pass. That's the ideal case if you take all the loop gain into account. And if it is an all pass, then you do not have any, means ideally you do not have any delay. Does that answer? Okay, we can talk of this later more, but we will look into this later in more detail. Okay. Anything else? So, yeah, this is a very bad line. Okay. So next topic will is oh, oscillators. So I think this will be the maybe the last big topic in charge from PLLs. Okay. So oscillator is any block or a block which an autonomous block, let me just say that, an autonomous block which produces periodic output voltage or current, whichever that is right now in material, because we are just looking for periodicity of current signal. Okay. So it is autonomous in the sense that an oscillator, it has no input as such you will see. It's not like a V in equals to V out kind of relationship. Okay. There will be different controls, but that will not be the case. Means the V into V out is not a case. So it has a V out, which you can say is something as a sine, means it can be a square wave, but the whole thing is it is periodic. Okay. And to have this periodicity means to sustain this periodicity in the system, the power it draws from the supply. So the interesting part is that there is no such V in which you see in normal circuit blocks. So this is the very basic definition for an oscillator, and we started when we started the PLL, we started that there is so different types of oscillators. So okay, well let me just say when I define this oscillator, so let's define some parameters here. Do you know all these, but just for the sake of completion. So a sine wave, the amplitude A of an oscillator is, this is A amplitude. I mean, these terms will come appear at many places. Amplitude A, oscillation frequency is F equals 1 by T, which is the time period, is omega by 2 pi. Omega naught, so this frequency F is in hertz, this is in per second, and this is in radian per second. Okay. This is the oscillation frequency and the relation. T is the time period. So these are just the general characteristics, and I think every one of you know about it. So there are different types of oscillators, and you know that the oscillator is the main block of the PLL because it only generates the source sinusoidal signal. Types of oscillator. So there are three main categories. One is the first one is crystal oscillator. Okay. So can anyone tell the different properties of crystal oscillator? So its crystal oscillator is like which may be present in your watch, or one crystal which is present as a reference source in all the synchronous systems. So what about the frequency of this oscillator? It's not it's not tunable once fabricated. You can during the fabrication you can tune it. So but the frequency of oscillation is generally low. It's a low frequency, not more than I think few megahertz or few hundred megahertz, maybe some extreme cases. Okay, but the frequency is very stable. The frequency doesn't change that much. So the other thing is it has stable frequency range, stable frequency, low frequency, and stable frequency means that the variation in the frequency of the crystal oscillator is very limited. So once you design a once you fabricate a crystal oscillator at a certain given frequency, it might not change more than 10 to 100 ppm max. Okay, and the other part is the phase noise is really good. So, and this is what we started was that you have a quartz crystal which has excellent phase noise, tuning range is very low, stable frequency or low frequency, and you can say limited tuning range, very low or limited tuning range. Okay, crystal oscillators. Sorry. Okay. The next one are your LC oscillators. So different kinds of LC oscillators are there, and you have Colpitt's oscillators. Means they here the oscillation. Let me just tell you, Colpitt's oscillator, Claps oscillator. So different kinds of LC oscillators are there, and they are based on the resonance frequency of a inductor and capacitor. So just to say, means all these LC oscillator they will have some component. Means these are the basic components for an LC oscillator which will be there, and here the tunable frequency is 1 by under root of LC. Okay. Here the resonance frequency, oscillation frequency is decided by an inductor and a capacitor parameter. Now this capacitor and inductor can come in any combination, and they will come with some active circuit elements also. So here means you can have high, means relatively high. So let's say uh, frequencies can be very high frequency of oscillation. But tuning range in this case is also limited. So moderate tuning range, and uh, frequency is stable but dependent on the variation in LNC parameters. So stability, moderate stability, I would say not that great as crystal. Maybe you can get up to 1000 ppm of variation depending on PVT variation, and phase noise is still good. So let's say, okay, let me write it as a, it's not excellent as your crystal oscillator, but it's still better. Okay. Then the third one of the oscillators are your ring oscillators, which are, so ring oscillators are based on your negative feedback. LC oscillators are also based on negative feedback. Ring oscillators mostly based on the delay in the loop. So let me show you. So this is an example. Okay, all these are connected to VDD and ground. So this is output. So this the oscillation frequency in a ring oscillator is the means this is still an approximation. It is inversely proportional to the delay of the each element in the loop. Okay. So this is not the difference between this and LC oscillator is this is based on the delay, the other one is based on the LC resonant frequency. Okay. And here you have it's like stability is poor. You need to control it. Is you can have more than a means I would say if you at a given voltage if you look for a PVT variations you can have a easily 50% of frequency variation depending on the uh, depending on the process temperature and other variation. Poor stability, so you need to control it, and it has poor phase noise I would say on its own, because you see this is here the oscillation is dependent on active elements which all contribute noise to the output, and that has a poor phase noise. The good part of this is wide tuning range. Means you can have an oscillator varying over 2x range easily in case of ring oscillators, which you cannot have in case of LC or resonators. Having a 2x range in LC oscillators is really difficult. Okay, and the other thing is this much smaller area. So this is actually smallest area I would say in comparison to the all the three. Okay. But another problem with this crystal oscillators is it's not easy to integrate in chips, and I would say, I mean, maybe some other cases, but not easy to integrate at all. LC oscillators you can integrate, but they occupy a large area. Okay. So these are three broad classification of oscillators, and now the thing is the analysis of oscillators is based on, or you can say, so let me just put it this way: in any given oscillator, any of these kinds, the question is always whether it will oscillate or not. So I am talking it's an oscillator, and I'm still asking a question: when and how will it oscillate, or whether it will oscillate or not? That question is quite valid. Okay. Oscillate or not? You need to figure this out. Then, what is the amplitude, frequency, and all the parameters actually? Amplitude, frequency, phase noise, or you can say phase noise or jitter, or those things, or timing error in oscillation. And the question is how wide is tuning range if it oscillates. The next two questions which are below, they are all dependent on first whether the oscillator should oscillate or not. And that question is answered actually in two ways. One way is okay. One way of analysis is your negative feedback, or means you see when the system will oscillate when it is connected in feedback. That's a negative feedback analysis. Okay, and the other way is negative impedance analysis. So these two are the two ways in which you can analyze oscillators, and one will lead to the other if you go in more detail. Okay. But in some case it is easier to do a negative feedback analysis, in some case it might be easier to do an LC resonator analysis, like negative impedance analysis. I will give you both the examples and then we will start with the negative feedback. So let me, I think this everyone will understand easily. So let's say I have an LC resonator, okay, and we know that if I give a certain voltage V at t time t equals to 0. So at t equals to 0, V of C V of 0 was, so let me just write V of 0, it's not coming right today, is V0, and I of L was equals to 0, right? And if this was an LC oscillator, that means there are no losses in the system, then you would say that this is going to oscillate with the frequency. So the final V out will be V naught sine of omega naught t, or here you can sine of omega naught t or cos of omega naught t, whichever. If I start with the highest voltage, it's because, okay. So, and omega naught is equals to under root 1 by LC. This, everyone is fine with this, right? How to find this differential solution for this LC resonator. Now the real systems always have a bad guy attached to it, and that is the loss in the system R. Okay, so if there is a loss in the system, what is the way? Means if you do not do anything, if this is an oscillator, then what you will see, the oscillations are actually die down. We will find all this through analysis, but let me, for now, this is the kind of the V out you will see. Even if you give a certain voltage to the capacitor at time t equals to 0, right? So without going to any mass, can you suggest what can I do to still make it oscillate? I got an unwanted R. What shall I do? Pardon? Add minus R to it. This is the easiest solution. Now, how do I get a minus R? Whether minus R is a physical or it's a passive or an active thing. How much minus R should be present at what instant of time? Okay. So all those things come, means all that analysis come with your negative impedance analysis. Okay, and that is very much mathematics involves. That's why I'm skipping for right now. I will come back to it once you get it through the negative feedback. Okay, any questions? Yeah. You can say that also. So right now I didn't bring any supply till now into the account, but all this energy has to come from somewhere. An oscillator cannot oscillate on its own without taking energy from anywhere. So what you are saying is, so there are two ways to look at it. Like one way is I can say cancel positive R with negative R, which is equivalent to saying is compensating loss, energy loss due to R. Just the two ways of saying it. Okay. Means cancel R plus minus R is more of an empirical. What we see in the formula, we can say I can just put a number there. Compensating energy loss is the real thing which you are doing in this oscillator. Okay. So we will look into this detail of this. The other case is, so let's say this is the negative feedback analysis. Negative feedback analysis of oscillation. So what we have, so we have a gain A. Let me just write it here. Okay, so one, this is negative, sorry, let me make it is positive, this is negative, and this one. So, okay, so if I give a sine wave at the input in response to the sine wave, so let's say you start with at time t equals to 0, you start with 0 here, you give sine wave at the input, then the wave appears here, it's multiplied by the gain, and then it depends what is the gain at that frequency in terms of phase and everything. You need to multiply it by the, because I am giving a one single frequency, so you need to see the phase and the magnitude gain and what you get at the output. So if I ask you that, okay, let me not ask this, let me say I get a certain phase offset or phase lag. I am deliberately drawing this. So what you get at the input when you come at negative here, right? So means I have to just invert that function. So what I have is something like this. Okay, so this is positive, this is negative. Will this make sense here? So what will come back again is the sum of these two, right, at the input. And if you want the system to oscillate on its own, the ideal thing is it should replace the actual input. Okay, because this is still very like hand waving here. So if I get, means if this wave is let me just something like this with a phase change of 180 degree, then after this negative feedback, what you will get at the output will be much larger version of, or whatever the version of this. So it will keep itself in the whole. So this oscillation is based on the negative feedback, and it is very much put down in terms of proper equations, which is Barkhausen criterion. Okay. And this is this actually states the necessary condition for sustained oscillations in a feedback system. Okay. So the condition is that if I have this as AS, and this is the feedback factor of the system, in that case, for the frequency at which the loop gain is equal to 1, so let me write it at the frequency of oscillation at which this loop is going to oscillate is j omega 0 times beta of j omega naught is equals to 1, and both should be satisfied, and the angle of a j omega naught times b j omega naught is equals to 2k pi, where k is equals to 0, 1, 2, etc. So I would like to say that this is the condition for a sustained oscillation, and this is the condition of equality. Okay. So do not take this equation that if it is greater than 1, it is unstable. If it is less than 1, it is stable. Do not make that inference from this equation. Pardon? No, because the thing is, if it is greater than 1, what do you mean by instability? Huh? No, but the thing is, it can blow up to infinity, but it can blow up to, it can have also a constant voltage, a constant current. It will go up to the maximum limit, but will it oscillate or not? The questions are the two things are different. When you say if the system is unstable, it may saturate, right? It may start from some value and saturate, but whether it is going to oscillate or not, can you comment on that? So the condition for oscillation is this. So the other thing is this you have to follow. Means this condition should be there to make the any feedback loop to oscillate, but this is not like a necessary and sufficient conditions. There are many other. There will be some other parameters also in the loop. So means that originally this came as a criterion for oscillations only, but people inferred it for stability and instability, which is wrong. That thing should not be. So you would have seen. So okay, let me just give an example, right? So you can have a gain greater than 1 and a phase more than 180 degree. When you start with the two-pole system, the phase is greater than 180 degree, and then you have a 0 where you have a loop gain equals to 1 and certain phase margin, right? So let me. So for a two-pole system or a type 2 PLL, you see. Okay, so not like this. Let's you consider another pole in the system, 3 poles in the system, that becomes much better. Okay, so then like this and like this. Okay, so I will very well have, so this, if this is the only loop gain, or this is the loop gain of the system, right? Omega u. The phase, where will I start with the phase for? This is minus 60 dB per decade, then minus 40, and here minus 20, right? And I can have the system as a very stable system. And in this case, what is the phase do I start with? Minus 270. I will go to minus 180. And since this is a negative feedback, there is another negative 180 degree phase. Okay, it's a PLL system. So in this case, you will start with minus 270, go to minus 180 and something. Let me just, I'm just saying that you can have somewhere as a phase minus 180 degree, okay, minus 270 and a gain greater than 1. But this system is a stable system. So, and this system will not oscillate also. Okay, if you have a certain phase margin. So let's start with another thing. There's time. Okay. Okay, let's start with the example tomorrow since time is running out. Okay, so we'll go with an example with this negative feedback oscillation tomorrow.